Let's start by doing some examples. I start by finding the power of a signal to show this Parseval relation. Find the power of this signal xt equals 1 plus sine omega naught t plus 2 plus sine omega naught t plus sine t omega naught t plus base rate 5/4. We need to find the power of this signal. So we have two options, as we have seen here in the Parseval's relation, either to do it in time domain or to represent the signal in frequency or in Fourier series domain, in frequency domain, using the Fourier series and calculate the power in the frequency domain by summing the power in each of the harmonics of the signal. So the two options here are either to do it in time domain, this is the fundamental period, do the integration over one period of the signal, and then xt absolute value squared dt. And it's clear that this is not easy in this signal, right? It's not easy to take the absolute value of the whole thing square and then find the integral of all. You would use multiple different things. And going to the frequency domain is much easier in this example. You'll do the k equals minus infinity to plus infinity, absolute value of ak squared. So it's in this example, it's easier to move to the frequency domain, represent this signal as a Fourier series, and then you need just to find the value of this summation to find the power of the signal. But before doing so, we can actually even simplify this equation. From here, from this property, we have seen that if xt is real, then the absolute value or the magnitude of ak, the coefficients, is even. Which means that ak equals a minus k, right? Yeah. If this is even, then ak equals a minus k, the absolute of the magnitude. So we can actually use this to simplify this term. We have this xt is real. Given signal is real. So this ak magnitude of ak is even. So let me rewrite it this way. This summation is just like we have a0 squared plus a1 squared plus a minus 1 squared plus a2 squared, and then plus a minus 2 squared, and so on. Since the signal is even, then this term is the same as this term. And this term is the same as this term, and so on. So we can rewrite this summation as this is the only one remaining, so we keep it outside. Plus, we have from each of those terms two equal terms. So we have 2 times We do the summation just from k equals 1 till infinity of ak squared. So we do the summation on just one side of the spectrum, and we multiply it by 2, and we add the 1 at 0. Good. So this one, this is the, let's say the power. This is the power. Now, all what we need to do is just to find those a's, and we are done. We know that xt, if we want to represent it using Fourier series in terms of those Fourier coefficients, it will be written this way: minus infinity to plus infinity, and then ak exponential jk omega naught t. Again, we can use this fact, the fact that those are even here. And you can write it in terms of just the positive ones, and we multiply by 2, right? But first, let's find first the fundamental frequency of this signal. Um, the period of what's the period of this signal? Fundamental period of this signal. The fundamental period of this signal is just 2 pi divided by omega naught. The same here, and the fundamental period of this signal is I'll call it T naught again. 2 pi over 2 omega naught, which is pi over omega naught, which is, let's call this one T1. So T1 is half T naught, because frequency, the, the frequency of this signal is double the frequency of this. Right. What will be the period of the whole signal? Let's call this one T1 and this one T2. T naught would be just the least common multiple of T1 and T2. And T naught would be least common multiple of T1 is 2 pi over omega naught, assuming omega naught is positive, and the other one is just pi over omega naught. What's the least common multiple of 2 pi omega naught and pi omega naught? You have an answer?
2 pi omega naught? Or is it just
It is um, the
or is it 2? My bad.
it's the 2 pi omega naught, right?
Yeah. Okay.
Yeah. So the period of the whole signal is 2 pi omega naught. And the frequency of the whole signal, the fundamental frequency is actually omega naught, right? So, so the fundamental frequency of the whole signal is omega naught.
Right.
And you have this slower frequency, and then you have doubled that added to the signal. The whole signal has a frequency of omega naught. So So in order to, now we have, yeah, so this is the omega naught. We can give it any number. Let's keep it omega naught for now. Here's the fundamental frequency of the signal, omega naught. And AK will be 1 over E naught times the integral over 1 period of the signal, xt, times minus J omega naught T dt. But if you remember from the last workshop, there's an easier way to do it for, especially for those signals that are just cosines and sines. This one will not affect the period or anything. It will just add a DC component to the Fourier series. So instead of, let's say, if we have a sine, which can be written or plotted this way, this is sine t. If we add 1 to this, if we add some constant 1 plus this, it will be shifted to be around 1. So it will look like this. It will be just shifted. Yeah, you got the idea, right?
Yeah, I think so. Yeah.
So it will be just shifted by 1.
Yeah.
Uh, So it will not affect it doesn't affect the frequency of the signal. It will add just we call it a DC component, a DC, which means it has the frequency 0. It doesn't have a period, its period is infinity and the frequency is 0. So we call it a DC component. There's an easier way to do this, as we have seen from the previous workshop. By using Euler's formula, we will rewrite each term of those. So I'll do easier method. Instead of doing this integral, the easy method is using Euler's. Using Euler's formula, the signal will be rewritten this way: 1 plus the first term was sine omega naught t. Sine omega naught t can be written as 1 over 2j, right? Initially j anything omega naught j omega naught t minus exponential minus j omega naught t, right? Okay. Great. Plus cosine cos 2 times cosine omega naught t, 2 times 2 times half exponential j omega naught t plus exponential minus j omega naught t, and those will cancel. We'll have exponential j omega naught t plus exponential minus j omega naught t. This is the cosine, and this was the sine. The last term is also a cosine, but we have a phase shift here by pi over 4. So we'll have plus 1/2 exponential j 2 omega naught t plus pi over 4. 2 omega naught t plus pi over 4 plus exponential minus j 2 omega naught t plus pi over 4. Now, let's try to simplify things. D1 plus 1 over 2j exponential j naught t minus 1 over 2j exponential minus j omega naught t plus exponential j omega naught t plus exponential minus j omega naught t plus, I'll take this outside, just my, I'll make it product of 2 exponentials. So I'll have 1/2 exponential j pi over 4 times exponential j 2 omega naught t, right? Plus 1/2 exponential minus j pi over 4 times exponential minus j 2 omega naught t. Now what's this term in this?
Is that like you can use Euler's formula for that for each of those?
Yes. So I write it as cosine pi over 4 plus j sine pi over 4. What's the value of this?
What's the value of what? Sorry.
Yeah, what's cosine pi?
Oh, square root of 2 over 2.
Sorry.
Is it square root of 2 over 2, I think?
Yeah, or just one divided by square root of 2.
Mhm.
It's the same as square root of 2 divided by 2. And the sine,
It's the same thing.
so yeah, let's continue here. This is just on the side, let's say, and then we continue. Let's combine those. Let's say here we have exponential j omega naught t, and this one is the same term. So if we combine them, we'll have this is the same. I'll keep it 1 plus 1 divided by 2j, and then here plus 1. So 1 divided by 2j plus 1 times exponential j omega naught t. And we have similar stuff also here, plus 1 minus 1 divided by 2j exponential minus j omega naught t. I will combine all this and this. For the last two terms, we'll have yes, 1/2 times 1 square root of 2 plus j over square root of 2 exponential j2 omega naught t plus. What about this one? What about this exponential minus j pi over 4? It's just the conjugate of this, the conjugate of the first term. So we write directly 1 square root of 2 minus j 1 square root of 2 exponential minus j 2 omega naught t. Now, can you see from here the Fourier series coefficients? Can you see them?
Only for like, actually, no. No, only for, I thought yeah, I think so. It's just that the J's, some are negative, some are positive.
Yeah. Yeah. So those terms, this one, this one, this one, and this one are the Fourier series coefficients. But we need to know which k is for, like, this is a k, but for which k, and for which k here, for which k here and here, and also this term. Can you tell this is which a, which?
That's K is 0,
Yeah,
right?
it's a0.
A
Because
0.
this is basically as if we are writing 1 times exponential j k omega naught t, but k equals 0. So this is just 1 multiplied by 1, right? K equals 0, so exponential 0 will be 1, and then, yes, this term is just the a0. What about the rest?
The second one would be A sub 1,
Yes,
and then the second one would be A sub 2. I mean, negative 1, my bad.
negative 1, yeah.
Yeah. And the next one would be A sub 2. And then the last one would be A sub negative 2.
Yeah, that's great. And we knew that by looking at those exponential. So this is the first harmonic. We are not multiplying the fundamental frequency, or we are multiplying the fundamental frequency by 1. So this is the first harmonic. This is the first harmonic, but minus 1. We are multiplying by k here is just minus 1. K. So here we have the fundamental frequency. Here we have negative the fundamental frequency. Here we have 2 times the fundamental frequency. So this is the second harmonic, k equals 2. And this is also the second harmonic, but negative 1. So with this, so it's k equals minus 2. We get the coefficients, and so the rest of the coefficients are zeros. Any ak when ak equals 0, when k is not, or let me write this way, k is not in this set of 0, negative plus 1, and negative plus 2. If k is not among those numbers, then the coefficient is 0. It's not there. We didn't see it. So, and also what we need for this specific question is just their magnitude. You see here, to find the power, we just need their magnitudes. So we need to find the magnitude for all of these numbers, for all of these coefficients, and then we will find the power. For A0, it's just 1, because it's a real number,
Yeah.
positive, so it's just 1. For A1, or let me find also the squares of them, right? It's easier, because we need the squares, we need the magnitude square, right? So if we directly find the squares of them, we get rid of the square root, because the magnitude of a plus jb, any complex number, is the square root of a plus b squared, right? But if I'm interested in the square of the magnitude, then we just get rid of this square root. So what's the magnitude squared of a1? A1 is here.
It would just be 1 over 2j squared plus 1 squared. Or
Not if you look here, look at this one. Without the j, we don't square. If we just square the real part plus square of the imaginary part
okay.
without the j. Because here, if you square the j, you will have 1 minus 1/4, which is not correct. We square the real part plus square of the imaginary part. And we don't do the square root because we are calculating the square of the magnitude. So this is just 1 square plus 1/2 squared, which is 1 plus 1/4, 1/4 or 1/4. And this is just 5/4.
Yeah.
5/4. What about this term?
It'd be the same value as a1 squared, right? Or
Yeah.
magnitude of a1
Yeah,
squared.
exactly. It's the same, because we actually used this fact here. We already used here. You remember when we expanded this summation, and then we said since xt is real, those terms will be, this term and this one will be the same. This will be the a2 magnitudes, the same as a minus 2 magnitude. So they are the same. So we just need to find a0, a1, and a2, and we are done. Now the a2 squared, a2 squared magnitude is the magnitude of this multiplied by 1/2, right? What's the magnitude of this complex number?
Just be 1, because it's 1/2 plus 1/2.
Yeah, that's correct. 1 and then multiplied by 1/2. Or like the magnitude, if I have, let's say, a complex number z, and I multiplied by I multiply it by a real number, and then I need to find the magnitude of the whole thing, then this will be just alpha times the magnitude of z. So this is the alpha here, is 1/2. So I multiply 1/2 by the magnitude of this complex number. So at the end, the magnitude of A2 will be 1/2 times 1. So 1/2. I write the whole thing. Which is 1/2 times 1, 1/2, which is the same as the magnitude of A minus 2. Right?
Mm-hmm. Yeah.
Mm, 5/4. Times 5/4, and then minus 2. Okay. A2 is 1/2 times 1, and then also this one is 1/2 times 1. Yeah, 1/2. Therefore, the power of the signal will be PT, or P is, as we said, A0 plus summation K equals 1 till infinity of AK squared. But in our case, um, K can be just 0 plus 1 minus 1 plus 1 minus plus minus 2. So summation when K is in plus minus 1 and plus minus 2. We have already taken care of 0. We can combine it with the rest. Okay, but okay, okay. Well, this summation will be, the first term will be just 1, 1. The second term is 5/4. Oh, we forgot the 2 here, right?
Mm-hmm.
Because we have two terms, and we combine them together. So we have 2 here. So 1 plus 2 times A1. Oh, I should write, yeah. The issue is that, did you see why? K here is just, we take the value of 1 or 2, not plus minus, not plus minus. Because we have already taken care of this, the negative terms, because they are the same as the positive K terms, and we already combined them. So we just need to add those positive side, and then we multiply by 2. 2 times A1 squared plus A2 squared. And this is the power, which is 1 plus 2 times A1 squared is 5/4 plus A2 squared is 1/2. So the power will be 1 plus 5 plus 1, right? So we combine them, so 2 plus 5 halves. 2 has 4 halves, so 9 halves, right? So which is just 4.5. So this is the power of the signal.